Hello everyone, welcome back to Physical Properties and Intermolecular Forces Part 2. So hopefully you already saw the first video where we talked about what intermolecular forces are, how to rank them, and basically how to identify them. And we talked a little bit about physical properties and the effects on melting and boiling point, but let's talk about it in a little bit more detail. So in the previous video, we talked about this slide already, so if this doesn't look familiar, you can always go back. But we talked about when you're ranking things in order of boiling or melting point, the first thing you want to look at is the strongest intermolecular force, and then if those are different, then you would do it based on the strength of those. So if I was comparing sodium chloride and water, those have different intermolecular forces, so the one that has the stronger of those two would be the higher boiling point or melting point. Then I also mentioned that there are exceptions to this rule. It's not always the strongest intermolecular force, and that size plays a role due to van der Waals forces. So if you're not sure on that, you can go look back. What we're going to focus on in this video is what about when there's a tie? So let's say we have two that have dipole-dipole, or two that have hydrogen bonding. Then what do we do? So let's look at those. So first we'll look at what happens if you have a tie between two with hydrogen bonding or a dipole-dipole. The first thing is there's actually two different situations for this. It matters which direction you're going on the periodic table, because in one direction we're going to look at the dipole, and in the other, dispersion is actually going to overwhelm that. So either way, we're going to use the periodic table. All right, so let's first look at across a row. If the difference is elements that are going across the row of the periodic table, then the more electronegative element is going to be a stronger dipole, and therefore it's going to win. It's going to have the stronger force. So this is because of the dipole. This is true even if you have hydrogen bonding and it's not dipole-dipole. Either way, that would be true. So if you're going across a row, like left to right, then that means that's going to be the difference. So an example of that would be H2O versus NH3. The difference there is nitrogen versus oxygen, and those are right next to each other on the periodic table. So if I wanted to know which of these would have the higher boiling point, I would look at the strength of the dipole. So in this case, oxygen is closer to fluorine, so it's more electronegative, so it would have the stronger dipole, and that means it would have the higher boiling point in this case because they're both liquids, and that's actually true. The other situation we can have is if we're going down a group on the periodic table. In that case, the larger atom is going to win, and that's because of dispersion forces. I should say that size increases as you go down the periodic table, because for each row of the periodic table, you're actually adding an extra electron shell. So because we're adding a whole shell of electrons on the outside of what we had before, that's going to be a lot larger. So the larger surface area is going to cause it to be able to be attracted that way, and that's going to be the difference. So an example here would be HCl versus HBr. The only difference is the halogen that's in that, and if you can see on the periodic table, those are different spaces on the periodic table. So if I was trying to figure out which of these would have the higher boiling point, I would look on the periodic table and see which one is larger. So that would mean the one that's the lowest on the periodic table. The one that's the biggest would be the bromine, and so that would have the higher boiling point. So hopefully that makes sense. Like I said, this will work for both hydrogen bonding ties or dipole-dipole ties. But if we have dispersion only, we're going to have to do one thing that's different. So let's look at that. So basically it's a similar idea. It's just if both of the molecules are dispersion only, they don't have any dipoles or anything, then that would just mean that the larger molecular weight wins. This is actually for the same reason. It's because the larger molecule has more surface area for dispersion. We're just using the molecular weight because weight is proportional to the size, and the molecular weight is something that's already totaled on the periodic table. So it's just an easier way to tell, but you can still go by how far away it is from the start at the periodic table. If you look at this example here, we've got H2 and I2, and they're actually not next to each other or down, they're both. But it doesn't matter, because if it's dispersion, it's just whichever one the molecule overall is the biggest is going to win. And a good way to see that easily is just to look at the molecular weight. So all of these molecules were written as their molecular formula and not drawn out. The same rules would apply for organic molecules that are shown in line bond form, so don't let that throw you. Just look for what's different about them. But then the other thing is there's some special cases for alkanes in particular. We'll get to this a little bit more later, but an alkane is just the part of the molecule that has carbon-carbon single bonds with hydrogens, and so we'll just talk about that because a lot of organic molecules have at least an alkane portion of them. So looking at this slide, we've got some alkanes shown here. As you can see, they're all carbon-carbon single bonds, so those zigzags, and there's hydrogens that are not shown, but there's no other elements. There's not any oxygens or nitrogens or anything like that. So an alkane, that's what that means, is it just doesn't have any other what we call functional groups. So here's the difference that we would compare. So there's two things that matter. If you're comparing the size of the chain, the number of carbons that are on there, that's going to matter. As you can see, we've got two different ones here. And then also the shape, the way they're connected matters. So if you look at the bottom examples, they're different connectivities. So let's look and see what the effect is. The first thing we'd want to do is think about what is the strongest intermolecular force for these molecules. So remember that we said carbon-hydrogen bonds are not considered polar bonds. That means that all alkanes are nonpolar, and that means they have dispersion or van der Waals forces. That would be their strongest intermolecular force. So we also said that dispersion forces, it matters how big something is or the surface area. So if we look at this molecule on the right, what happens is whenever you have this molecule plus another one of the same, so let's maybe draw that here, each of these CH2 groups are going to have an interaction that's called an induced dipole. Basically what that means is that even though the molecule overall is not positive or negative, even if the bonds aren't, the electrons can be shifted around by being close to each other. So I'm going to draw these as circles, so pretend these CH2 groups are circles. All right, so on one side, just for one moment in time, let's say that the electrons happen to be leaning in one direction. So let's say they happen to be leaning down. That would give us what's called a partial negative charge. This little symbol here for the sigma means partial. So it's a partial negative and a partial positive. It's temporary, it can change, but that's what it is right now. As soon as that happens, the other molecule is going to see those electrons from the partial negative, and they're going to be repelled because that's what electrons do, and it's going to push them to the other side. So that's going to make an induced dipole for the molecule that's right next to it. And then what will happen is all along this back chain, you'll get a partial negative on this side for this molecule, which will then cause this other one to have a partial positive, and then they'll just line up like that. So my professor always explained to me as it's like a zipper. Once you get started, it'll actually want to be close to each other, and they'll be attracted because of that induced dipole. And so then they'll basically zip up and they'll like line up. And so you'll have interactions in between those two molecules like that. So now if we understand what the induced dipole is doing for these alkanes, we can start to see why the size and shape matter. So if you look at these molecules for the size, the one on the left can make a zipper, but it's going to be a smaller zipper, right? But the one on the right is going to make this long zipper, and then it can just keep doing that with the other molecules. And so those are going to be more closely held together and tighter, and they're going to be harder to move around, because even if I break one of those edges, it's just going to zip right back up. Whereas if the short one, if I break one of those edges, it's more likely to be able to get away and then completely tear off from there and not be interacting anymore. Another good analogy is if you think about Velcro. If you have a tiny square of Velcro, it's actually pretty easy to get those two things apart. But if you have a long strip of Velcro, it's actually really hard to get it open because there's just more surface area that you have to break the interactions. So what does all this mean? Well, basically it means that the longer carbon chains are going to have higher boiling points. So between these two, this one has the higher boiling point, as you can see if you look up the experimental data. So now we can apply the same logic when we look at the bottom two examples to see that the shape matters. So again, if we're using the zipper idea, which one of these would be able to make a better zipper? Right? Obviously it's going to be the one on the left because it can line up the way we described. The one on the right is actually going to make more of a ball shape because of the way the surface area is laid out. So we're going to have to try to get it together, but there's just not as much contact that you can have. As you can see, no matter how I do it, I can't get as many contacts. Even though if you count it, both of these molecules have the same number of carbons. So it's not a size issue, it's just the shape, and that changes the surface area. So the lower surface area will result in a lower intermolecular force. Now, we call this branching. So basically the one on the left has no branches, and then the one on the right has branching. So what we say is the more branching you have, the lower the melting point or boiling point. So that means between these two, which should have the higher boiling point? Right, it'd be the one on the left. And we see, again, experimental data says that's the case. So now that's it for all the tiebreakers for melting point, boiling point. So let's talk about something else. So really quickly, let's talk about solubility. You've probably all heard the solubility rule, which is like dissolves like, but what does that mean? Like what? So when we say like dissolves like, what we mean is the intermolecular forces. Basically, if you have similar intermolecular forces, they're more likely to want to stay together. So this is going to be really similar to the ranking problems that we already did. There's just going to be slightly different trends depending on what your solvent is. So let's look at that. So as you may remember, we said that these were the intermolecular forces and that these were the rankings. So ionic would be the strongest and dispersion would be the weakest. So when we were looking at melting point, boiling point, that's what we are looking at. Stronger intermolecular forces will have higher melting points. For solubility, it's a little bit different. The first thing is, whenever you're doing solubility, you're usually not thinking about ionic interactions. They're actually ion dipole, which means one of them is an ion and one of them is not an ion, it's something else. So then that's a slight difference. But if you take these forces and divide them up, 1, 2, and 3 are all considered what's polar. So if you hear something as a polar molecule, any of those can still be called polar. The bottom one alone is the only one that would be considered nonpolar, and that's how we'll divide them when we talk about solubility. So when we look at that, polar things are going to want to dissolve with polar things, and nonpolar things are going to dissolve with nonpolar things. So probably the easiest way to see how we're going to do this is to just work through problems. So let's do that on the next slide. So the problem would be rank these molecules in the order of decreasing solubility in water, first of all. This means we're going to rank them from most soluble in water to least soluble in water. The first one's going to be the most soluble. So looking at this, let's first identify their strongest intermolecular force for each molecule, and then that's going to help us rank them. So now I want you to pause the video and take a minute to identify the strongest intermolecular force for each of these molecules. Is this what you got? Hopefully it is, but if not, you can go back and review the previous video where we talk about how to identify the strongest intermolecular force, because that's really important. So now that we have done it, we're basically going to rank these and then figure out if that's going to help them or not help them being soluble in water. So what you would need to do is rank these in order from strongest intermolecular force to weakest intermolecular force. Pause the video and do that now. So if we look, the strongest intermolecular force for this one would be this magnesium bromide, and then the weakest would be the bromine. So what we find is that if it's in water, the strongest ones are the polar ones, right? So the more polar something is, the more soluble it is in water. And that's especially even for the ions, because they make ion dipoles with water, it makes a stronger force. So the ranking's going to be the same order that we would have had for melting point, boiling point, which is kind of cool. So then that would be the order. Now let's look at a different solvent. So for this problem where I'm ranking the decreasing solubility in hexane this time, I'm first going to have to know what hexane is. So hexane just means it's a 6-carbon chain, so it would look like this, and then that's an alkane, so that's where it gets that name. We'll talk about naming later, but for now you only have to know hexane, or I'll draw the structure. So this is hexane. So for this problem, I'm going to go through all the same steps, but then the last part's going to be a little bit different. So let me put that information back. So now I've got all my intermolecular forces, I've done all my ranking of strength. The only difference here is that hexane has what kind of forces? Hexane would be all dispersion, right? Because it's got no polar bonds. So that means that it's dispersion, it's actually nonpolar. For a nonpolar solvent like this, it's not going to want something that's superpolar. That's actually bad for it. The one that would be the most soluble would be the van der Waals, right? But it's actually an inverse effect. So the one that would be the second best would be dipole-dipole, because at least it's not so superpolar. So the more polar it is, the worse it is for hexane. So the rankings would look like this. So now we see that van der Waals, the bromine, would be the most soluble in hexane, and then the ions would be the least soluble in hexane. So it's just the exact opposite of all the other ranking problems that we've done. And with that, we are done talking about solubility, so we're done with intermolecular forces and properties for today. That's the end of this video. If you have any questions, feel free to ask me in class, or you can email me and ask me as well. So hopefully this was helpful. Have a great day. Bye.